These notes are over ionic bonds. So these bonds are chemical bonds that are formed between ions. And so we talked about ions in the last section, how ions are losing or gaining electrons. So atoms in an ionic bond, they actually transfer electrons to the partnering atom. So either going to give electrons or the other one would take electrons, causing the atoms to become positively or negatively charged. And because they become opposite charges, they actually have this bond that brings them together that forms this ionic bond. Okay, so the positive and negative charges that are left over because one atom is giving their electrons and one atom is taking the electrons causes these ionic bonds to form. So ionic bonds form between metals and nonmetals. So we can easily look at a chemical formula and determine, is this an ionic bond, by looking if the two elements that are listed are metals and nonmetals. Okay, so from the periodic table, if we had, let's say, calcium and oxygen mixed together, okay, here are all my nonmetals, and you'll see that oxygen, which is element number 8, is in fact a nonmetal, and then calcium, which is element number 20, is a metal. So this would be between a metal and a nonmetal. It would be considered an ionic bond. Ionic bonds form crystal solids that have very high melting points, but these crystals are brittle. So one classic example of an ionic bond is sodium chloride. So if I look at my periodic table, sodium, which is over here in the metal section, and then chlorine, which if I highlight my nonmetals up here, is in fact a nonmetal, so it is an ionic bond. Sodium chloride is table salt, and so if you look at the structure of table salt, like under a microscope, you can see that it does have a crystal shape, but it is very brittle. You could smash it with a hammer and it would kind of just shatter. When some of these crystals that are formed with ionic bonds are dissolved in water, they actually break up into their individual ion components and become electrolytes. So you've probably heard the term electrolytes before when you've heard about like sports drinks or like Gatorade. And so what it is they've taken these ionic crystal solids and they've dissolved them in water, and it produces these electrolytes. And these electrolytes actually help conduct electricity. So in our body, our muscles actually have these impulses, which are kind of like electricity that go across them in order to have them contract or release. And so the electrolytes actually just help to make sure that that goes smoothly, that you don't have any cramps whenever you're like working out. So we can actually determine the chemical formula of an ionic compound if we know the elements that are going to be combined. First off, we know that one has to be a metal, one has to be a nonmetal, but we can predict the formula based on the oxidation number. So if we were going to chemically combine potassium and oxygen, if I look on the periodic table, potassium is in the metals, and then oxygen is in the nonmetals. Here it is there. We're going to figure out what the chemical formula is, okay? So we need to know the oxidation of each number. So I have a chart here that has the oxidation number. And I have this chart on the previous notes as well. It says that it's only +4, but it is plus or -4 in this column here. But you'll see that in my first column, it has an oxidation number of +1, meaning that it's going to give away one of its valence electrons. For column 2, it's a +2 oxidation number, meaning it's going to give away 2 of its electrons. Okay, we skip to column 13. It's a +3. It's going to give away 3 electrons. Column 4 can either take or give 4 electrons. And then this is where we flip, where column 15 has oxidation of -3. And so it's going to take 3 electrons or gain 3 electrons Column 16 is a -2, it's going to gain 2 electrons. Column 17 is a -1, it's going to gain 1 electron. And then our final column 18, our noble gases, has an oxidation of 0 because they do not bond with any of them. They're already happy, they're not going to give or take any more electrons. So for step number 1, we're going to write the elements with their oxidation number as a superscript. So super means upper, the upper part. So here I have my K, which is for potassium, and then the oxidation number for K is +1, and then I wrote out my oxygen, and then its oxidation number is -2. So I just got that straight from this chart. If you find K, it's in column 1, so it has oxidation of +1, and then O, which is in column 16, has an oxidation of -2. For the second step, we're going to cross the numbers of the oxidation numbers so they become the subscripts of the other element. Okay, so this oxidation that we had for potassium is going to drop to become the subscript of oxygen, and then this oxidation number of oxygen is going to cross over and drop to be the subscript of potassium. Okay, for step 3, we're going to remove the negative and positive sign and put together the elements with their new subscripts. Okay, the metal always gets listed first. So in this case, we have potassium already listed first. We're going to smush these together, take away the signs, the negative and positive sign, and then remember that if a subscript is 1, we just leave that off, so it becomes an imaginary 1. Also, what I do want to say about this, so this would be the chemical formula for potassium and oxygen together, but if for some reason, if we were doing, so let's say we're doing magnesium and oxygen, so magnesium has an oxidation of +2. So if I were to drop it down, drop this one down, I would have Mg2O2, okay, but my subscripts in this case I would reduce. Okay, so they're both divisible by 2, so I would just get MgO as my final answer because it would reduce down into 1 magnesium and 1 oxygen.